This is a study of palladium-boron material made by Dr. Imam, and Martin Fleischmann helped with the analysis of the experiment. The experiment was done in Japan, at NHE in Japan, or at least some of it was done in Japan. It was first started in China Lake, actually. It was on an ONR-funded program with Fred Sawfield. He was head of ONR. He was interested in this field, and he helped this field out for 3 or 4 years. The Navy program involved NRL, China Lake, and San Diego in those years. But one of the functions was for NRL to make their own material because we knew the material was a critical factor. So we made various materials, but the only one that worked well was the palladium boron that was made by Dr. Imam. Other materials he made did not work nearly as well. So he could describe the preparation, but this is the way he prepared it. He would arc melt it at a high temperature with high purity palladium, and he'd add boron, a small amount, less than 1%, like he said, and other amounts even smaller, or down to about 0.2%, which is smaller, right? And just to show that in many experiments we don't get excess power. This is what it looks like when we don't get excess power. He first made palladium silver that we tested at China Lake, and you see there's probably more points below the break-even line because we overcompensate for any possible errors. But as soon as we went to the palladium boron, you see most of the points start being above the line. This is excess energy, excess power. This was the first experiment we ran. This is kind of an order of how we did the experiments. This was the first effect, and yes, we had excess power. We went to another sample. This was probably one of the best samples we saw. One thing, this excess power starts early with the palladium boron. You don't have to wait a week or 2 weeks. Within a few days after you load it, you start getting the excess power quite early. To show you that not every experiment worked, 7 out of 8 gave excess power. There's one that did not. And this had a region that was, when it was swaged one side over another, it kind of swaged over and formed like a crack. And I knew that was probably in trouble when I saw it, but I couldn't do anything about it. And with that sort of crack, it did not give any excess power. Maybe a little bit, but it's not enough to really say excess power.
I got a question for you. You're saying that one didn't give any excess power, but I see a lot of stuff above the line.
Yeah, but it's not quite convincing. I would say, yes, there's more points above the line than well, you might say small excess power, but it was not high enough that I wanted to claim excess power. Most of the lines are below maybe 50 milliwatts. I like to see my error was plus or minus 20 milliwatts, and I'd like to see more than 50 milliwatts to say excess power. So it was really borderline. Maybe there was some there. This is a less amount of palladium in the material, 50.5 weight percent. Again, we see nearly every experiment it shows the effect. It shows the effect early, within a few days after you start the experiment. As soon as you get some loading, you see the excess power. This is another study, another sample of the same composition. We even went down to 0.25 weight percent. This is the lowest that we did. And we still see the excess power, even without that small amount. But if you calculate it out, even that small weight percent, it is still about 1 atom of boron for every 10 atoms of palladium on an atom-to-atom basis. The boron is so light, the weight percent is quite low. Here's an experiment that started off excess power, then for some reason it dropped off. And you see it's pretty well no excess power. It lasted about maybe 4 or 5 days to get excess power. Then it went away. Why, I don't know. But most of the time, if the excess power would stay as long as you wanted to run the experiment, you'd keep getting excess power. Later, I went to Japan, and I took a new sample that I had never run before, and I wanted to see what it would do. I took it to Japan, and it gave excess power very early. This was different calorimetry. This was Fleischmann-Pons calorimetry, more accurate than what I was using.
Where's the baseline on that?
It's right here. This is, if I put the baseline, you see almost all of that is above the baseline. That's the zero line right there. This same data set, I later got the computer data set, and I turned it over to Martin Fleischmann. One data point every 5 minutes, day and night, over this entire period, and so he could do his analysis. This is just my lab book analysis. This is the complete computer data that Martin Fleischmann did in a completely different way. We did very independent analysis. I used one method and he used another method. You still see this sharp peak here, you see this sharp peak here. You see these peaks up and down here, up and down here. You see this region here of peaks, this region of peaks. I mean, totally independent. This is a very similar results that we came up with. His is more accurate. No question Martin does a better job, because he's been doing this for a lot more years than I have. This was my first exposure to this calorimetry, and I had to work out my own methods. I didn't know how to do it any better, but it still worked out pretty well. This illustrates, this is just the temperature. This is the heating pulse comes on, the temperature goes up for 6 hours, then it goes off, and the temperature falls down. But this shows you a simple way to see whether you have excess power developed through the heating power. Here's the baseline of temperature. If there's no excess power, you extrapolate this over, it comes down to the same baseline. You see, this did not come down to the same baseline. It's a little bit above. You don't even have to do calculations. You don't have to do mathematics. You just draw a baseline, and if it doesn't come back to the same baseline, that's excess power. And you do the calculations, it proves it's excess power. But that's a simple way without any math, any equations. If it does not relax back to the same baseline, you have excess power. And with excess power increased during the heating pulse. And we saw this many times with this experiment, but other experiments, it always comes back to the same baseline. It's only when you have excess power that you see this, where it doesn't relax back. At the end of this experiment in Japan, we boiled it off. You can't read this. This is Martin Fleischmann's graphs, and they're not very clear. But the excess power, as the temperature went up, and we started to boil the solution, the excess power went higher and higher. This point is about 10 watts of excess power. And I could see the inside the cell, because this is a Duraglass cell. And when it was boiling, everything was swirling around the cathode. The cathode was obviously the hot point inside the cell.
Two questions about the 10 watts. How long into the experiment did you start seeing that level, and how long did it run for?
We tried to keep it from boiling up to about the end of the experiment. So it was about the 65th day in the experiment. But we didn't want it to boil until I got through the experiment. Only then did I allow the temperature to keep going up. Other times I turned it down in order to kind of kill the power a little bit.
How did you turn the input current
you just
down?
You turn the current down, and then the power would drop. So I tried to keep it from boiling so I could do the study for longer. But finally I just let it run on its own, and I actually turned the current up a little bit higher, and it went into boiling.
So about how long did it run, I guess close to boiling, you're saying?
The boiling took about 2 or 3 hours for it to boil dry. It would boil completely dry over a 2 or 3 hour period. As soon as it boils dry, the electrolysis stops. There's no more electrolyte in there.
Right.
So the current goes to 0. So you're not putting any more power in at that point.
Do you remember approximately what the current and the volts were? A general range?
Probably less than 1 amp, about 0.8 amps, 800 milliamps to drive it up to boiling. It was higher, one of the higher currents we used, and that drove it into boiling. But this is Martin's excess power. You see, over this 3 or 4 hour period, it really soared up during this boiling period. And once it boiled dry and there's no power added, this excess power continued for 2 or 3 hours. That's called the heat after death. You can't see that too clearly on here, but it didn't drop to 0 right away. It took 2 or 3 hours for it to come back down. So you had it with no electrolysis going on, no power being added. It still produced excess power for several hours afterwards. This just shows you another experiment, the NRL plating cerium boron, that where I did analysis like I did here. There's no excess power, or not very much. There's fluctuations. I have more error in my analysis than Martin does. You see Martin's analysis, he never goes below 0. It dropped down to 0 at one point, and then but there's never anything below 0, because getting less power out than you put in is not really possible, certainly on thermodynamics. But if you see power below what you put in, that's your error. You have some error going on. But it still averages out about 0 excess power here. The frustrating thing about this is other laboratories have tried this. It might have been a different plate and boron sample, but EarthTech, Scott Little and Dennis Letts tried to run the experiment. I went there and helped them set it up. but they did not get any excess power in their experiment. It was a rainy, humid day, and in my opinion, the reason for the no excess power is they had trouble getting the cell installed, get the lid on just right. The cell was sitting open for a lot longer than I'd ever allowed it to be sitting open, and picking up moisture from the air. And then it's a closed system, so once they close it up, that light water, regular water, never gets out. And I think that's what stopped their experiment from succeeding. Now, Ed Storms also tried 2 samples, and he did not get excess power, and I don't understand why, but he uses a closed system. So people using closed systems, they haven't succeeded with this, getting this excess power.
Do you think it means anything relative to yours?
It means you better be very careful, make sure everything is pure, that you don't have any water in your decoke, because once you close it up, it's never going to purify itself.
Was this a second batch of alloy?
Dr. Imam, what do you think? Do you think it's the second batch or another batch? He said it's possibly a different batch. Hard to tell, but he made it in 2003. This is 2003, much later in time, that we did this study with Scott Little, Dennis Letts.
How come Imam won't talk to us on camera?
He might get in trouble.
Why?
He has to deal with people in NRL.
All right.
I guess, I don't know. He wants to keep his job. Maybe. But I point out one thing I thought was very interesting. When Martin analyzed this data, he would see when the power would drop down like this, he would say, you must have opened a new bottle of heavy water and it was contaminated. And I went back and checked my notebook. Yes, on that day I opened a new bottle of heavy water and Martin could tell it was contaminated, and it kills the excess power effect. He was able to pick up little things like that with his analysis. When I opened a new bottle and when the effect dropped. So that's amazing to me. But it shows you that light water contamination is a serious problem that stops the effect. Right. So that's about all I have to say.
Great.
Unless you have any questions.
That's good.